Hello everyone, today we are going to be talking about the 2025 question number 2 FRQ on the AB portion. This was a graph and calculator question and it only showed up on AB, not BC. So let's get along and let's dive into this question. All right, so let's talk about this. Our question is number 2. Okay, and again, this is a graph and calculator for the AB portion. So the shaded region R is bounded by the graphs of the functions f and g, where f of x is x squared minus 2x, and g of x is equal to x plus sine of pi over x, as shown in the figure, okay? So let's quickly just talk about this figure. We are given R, which is this whole region here, bounded by 2 curves. Our top curve is g of x here. It's consistently the top all the way from 0 to 3. And our bottom curve is f of x. Okay, notice our shaded region starts when x is equal to 0 and ends when x is equal to 3. All right, let's go into question number 1. So the first question is find the area of region R, show the setup of your calculations. Okay, immediately I need to know that, hey, how do I find the area between curves? Okay, that is simply just taking the integral from a to b of your top function minus your bottom function and having our dx there, okay? So let's do that. Let's ask ourselves, what's our top function here? What is our bottom function? Okay, so our top function is g of x, so I'm gonna have integral g of x minus our bottom function, which is f of x dx, and I need my bounds, and my bounds in this case are going to be from 0 to 3, because that is where our region starts x-wise, is at 0, and our region ends at 3. Now, you can input the functions on paper, so I can do integral 0 to 3 of whatever our g of x function is. Our g of x function is x plus sine of x, so x plus sine of pi x minus our lower function, which is x squared minus 2x, x squared minus 2x dx, and that's what you can put into the calculator. You could do that, or you could do the method that I like, which is banking your functions. So first thing let's do, let's type our functions into DESMOS quick. So f of x, f parentheses x, is equal to x squared and then minus 2x, okay, g of x, let's put that sucker in, and that is equal to x plus, I forgot I said equals, my bad, x plus sine of pi x. I'm going to physically type the word pi in, and DESMOS already knows, hey, they're just doing the pi symbol. Okay, if we zoom in on this side, we should be getting the general shape of our graph, if we are. Now, let's put our statement into DESMOS. So that is the integral, so int, going from 0 to 3, of parentheses, our first function, our top function here, which is g of x minus f of x, big parenthesis, and we got to put dx. All right, and we get the answer to be 5.136. Again, with AP, you do not need to round at all. You just need the 3 decimal places, and then you get to drop. All right, so that is problem number 1. Let's go to problem number 2, part B. So region R is a base of a solid. Okay, so we're just going to talk about bases of solid and volume now. For the solid, at each x, the cross section of the perpendicular to the x-axis is a rectangle with height x and the base of region R. Okay, right there. Our region is going to be a rectangle, so I need to figure out, hey, what is my area of a rectangle? That is length times width, or in our case, I can rewrite that and think that as base times height because that's what they give us, our base of our rectangle and then our height of our rectangle. Now, what is our base in this case? They tell us our base is region R. Region R is given by g of x minus f of x. So if I draw any vertical line there, that is represented by g of x minus f of x. Now our height is also given. Our height is given height of x. Now, if we want to figure out the volume of a solid, all we got to do is we got to integrate our area equation with respect to x. So in this case, we're going to integrate our base times height. Our base is g of x minus f of x times x for our heights, and we're going to integrate that with respect to dx, and that is from 0 to 3 again. Let's put that into our calculator. Notice I only have to change our x there, add an x, because we already have g of x minus f of x. That simplifies to, that is 7.704. It's just like that. We found the volume of our shape there. Okay. Right, do not, for C, right, but do not evaluate. Okay, so we do not have to plug anything into the calculator. An integral expression for the volume of a solid region generated when the region is rotated around the horizontal line y is equal to -2. So immediately I know that there is going to be a horizontal line at that y is equal to -2. And what we're doing is we are rotating around. Now, right there, I'm thinking of the disk and the washer method. The disk method is when we have no missing area or no missing section. And the washer method is when we're going to have a missing section with a radius. So let's draw a line to any part of our top of our region R. Notice we have a missing gap in between this section right here. So we're going to have to do the washer method. Now the washer method is simply just our big radius squared minus our small radius squared. Why is that? Okay, it's the idea of we are taking the circle, and what we're doing is we're finding the area of the circle, which is pi r squared. That pi is just a constant, so it can be removed. And what we're doing is then we're taking the bigger area, so the top function area, and we're integrating that, so we're finding the volume of our bigger figure, and then we're subtracting the smaller section, that highlighted section, that distance and that radius, and that area as well. So our integral would turn out to be integral from 0 to 3. We have a pi. I'm just going to write that pi completely on the outside. One big set of parentheses. Now we need our first radius squared. So our big R squared minus our little r squared dx. All right, so now we need to figure out that distance. Okay, so that distance for our top function would be from the top of our curve to -2. So immediately I know, hey, the top section is always represented by g of x minus -2, because we are subtracting the negative value. And our bottom section is going to be our lower function. In this case, that is f of x minus -2. And just like that, that is our washer method, and that is to get the area under the volume of our section if we were trying to rotate around the horizontal line y is equal to -2. All right, last but not least, this one's a little interesting. I thought this was very interesting when I first saw this FRQ. It's a little bit different than what you usually see on these area of questions. So it can be shown that g prime, the change of g, is equal to 1 plus pi cosine of pi x. the value x for 0 to x, which is less than 1, at which the line is tangent to the graph, is parallel to the line tangent to the graph g. Let's rephrase that. Let's reset that again. Define the value x. So we are trying to find at what x is which the line tangent to the graph of f is equal to the line tangent to the graph of g, okay? Or it's parallel, meaning parallel lines have the same exact slope, meaning, hey, at this x value, at x, we know that g prime of x has to also be equivalent to f prime of x, aka their slopes have to be the same. So what we're going to do is we're just going to graph g prime and f prime into my DESMOS calculator and say, hey, when are they intersecting? So let's do that. So g prime of x, we got that function graphed, and let's graph f prime of x. All right, I'm only going to show the ones that we want. All right, we are looking in between 0 and 1. So we are looking between 0 and this line right here. Click where they intersect. And that is going to be at the x value of 0.675. So at x equals 0.675. All right, and let's just think about that logically real fast, right? We are trying to figure out at what line tangent to the graph of g is parallel to the line tangent graph of g, to f. So we're saying a little bit past halfway between 0 and 1, so about like right here, if I would draw those tangent lines, they will be parallel, aka they had the same slope. So if I would sketch those curves, we would have them being parallel. All right, and that is all of those FRQ parts answered. Okay, this was a pretty straightforward question. You just really had to know your way around area, volume of 3D shapes. Okay, let's see how they graded. All right, so let's talk about how the AP graders graded this FRQ. Okay, so the first problem, problem A, it says find the area of R, show your setup. So what we did was we did the integral from top to bottom of dx. So the AP graders gave 1 point if you correctly labeled integral from 0 to 3 of g of x minus f of x. So you got 1 point for that part of your answer, and you also got 1 point for your answer of 1.36. You also would have got a point if you would have plugged in your functions, but again, if you just label them g and f, it's a lot easier to notate and it saves you a lot of time. All right, let's go to problem number 2. Okay, you got a problem, an answer, some points. You got 1 point if you had the correct integral. And you also got another point if you got the answer of 7.704. Let's move on to question C. Now, this one's interesting. You got a point if you use the idea of your big radius minus your small radius. So you got 1 point for using the washer method. So that was pretty nice of them. You got another point for your integrand, for doing having the correct integral, not the bounds, just the integral. And then you also got a point if you had your pi as your constant and your correct bounds. So this question was worth 3 points right there that they gave out pretty much if you just understand what you're doing with the washer method. And then lastly, the last problem, you got a point if you set g prime is equal to f prime. That was 1 point. And you also got another point if you said 0.67 was your answer. All right, and so those are all of how, that is how the AP graders graded this AP FRQ. They were pretty generous, and I feel like with the with the area and volume questions, they are pretty generous. They give a lot of points for having the correct bounds or the constant out front. So when in doubt, if you forget the area and volume, make sure you have those bounds down and the coefficients if you need those coefficients. Okay, and just like that, we are finished with this FRQ. It was a pretty straightforward problem. It was just dealing with area and volume, dealing with some 3D shapes, and dealing with a washer method rotation. So I hope you found this video helpful. I hope you are finding this whole series helpful. There are plenty more videos to come, and I hope you guys are having fun studying for this AP test, and I hope you're learning a lot. All right, so go check out another video. I hope you have a great day.